Good day everyone, let us continue our discussion with the fourth unit. Which is the basic knowledge and skills in electricity. What is electricity? As cited by Bernard Grove in 2009, electricity is an individual force that can produce heat, motion, and many other physical effects. The force is an attractive or repulsion between electric charges. It can be explained in terms of electrical charge, current, voltage, and resistance. The corresponding electrical units are the coulombs for measuring charge, the ampere for current, the volt for potential difference, and the ohm for resistance. Let us start with the basic electrical symbols that contain earth, electrode, cell, battery, resistor, etc. Whether you are a novice or professional engineer, these basic symbols can help create accurate electrical and circuit diagrams in minutes. You can depict a complex electrical circuit with a standard and simplified electrical symbols. Therefore, anyone who knows of electrical and electronic circuits can read, understand, and build electrical diagrams quickly. Electrical symbols are the standard technique to represent an electrical circuit. It makes the graphical representation easier to work on and implement. The electrical symbols represent various components, devices, and functionalities present in a circuit. It helps to show the details of an electrical diagram so that the engineer can adequately plan a circuit before actually working on it. Here are some of the basic electrical symbols. For passive components, active components, digital electronic, electrical test and control equipment, and other electrical and electronic symbols. The basic units of a simple electrical circuit are the ampere, volt, and ohm. A simple circuit typically consists of a voltage supply, metal wires that conduct the electrical current, and one or more resistors that resist the conduction of the current. The current may be direct current or DC, or alternating current AC, and there should be no additional devices that affect the current. The unit for electrical current, the ampere, is the basic international standards or SI unit. The voltage unit and resistance unit are derived from the ampere and other standard units. The ampere is a basic SI unit of electrical current. It can be defined as the amount of electrical charge of number of electrons that pass a point in a circuit in 1 second. 1 ampere equals 6.241 electrons passing a point per second, or 1 coulomb per second. The electrical current on the load is measured to help an ammeter by connecting it in a series to the load. It has zero resistance and so measured circuit remains unaffected. The volt is the derived SI unit of electrical potential, all electromotive force that causes the electrons to move. Since a source of electricity creates energy, a volt can be defined as the potential difference between 2 points in an electrical circuit that will impart 1 joule of energy per coulomb of charge that passes through it. Voltmeter is a device used to measure the difference in electrical potential between 2 places, such as 2 points within a circuit. A voltmeter is a two-terminal device, one connected towards another to leads. Ohm. Ohm is the unit of electrical resistance in a circuit. It is defined as a resistance between 2 points of a conductor when a constant potential difference of 1 volt applied to these points produces in the conductor a current of 1.0 ampere, provided the conductor is not the source of any electromotive force such as in a battery. An ohmmeter is a device used for measuring a material's electrical resistance, which represents the opposition it presents to electrical current flow. This instrument consists of a variable resistor, a meter movement that is calibrated in ohms, and a battery. Ohm's law. is the most fundamental formula for simple electrical circuits. It states that the electrical current passing through a conductor is directly proportional to the potential difference across the conductor. It was first formulated in 1827 by German physicist George Ohm while doing experiments on how well metals conducted electricity. Here's the Ohm's triangle, a visual representation of Ohm's law, which makes it easy to understand it. Let's consider a triangle with three levels, V, I, and R. Ohm's law's triangle can easily be used to obtain three equations. To find voltage, V is equal to IR, or voltage is equal to current multiplied resistance. To find current, I is equals to V divided by R. Current is equals to voltage divided by resistance. To find resistance, R is equal to voltage over R, or resistance is equals to voltage over current. For example,
so you just need to remember these three letters in order, V, I, R. Then we just write those letters in a triangle with V at the top, and we draw a line to separate the letters. Now all we do when we need to use a formula is cover up the letter we need. So if we want to find the voltage, then we write V equals, and then we cover up the V in a triangle. That leaves us with I and R, so we write I multiplied by R, which means voltage equals current multiplied by resistance. You can write a little multiplication symbol in the triangle between the two letters if it helps you. Now I know what you're thinking, why is current represented with the letter I and not a C for current, or even a letter A for the unit of ampere? Well, the unit of current is the ampere, or the amp, and this is named after André Ampère, a French physicist. A couple of hundred years ago, he undertook lots of experiments, many involved varying the amount of electrical current. So he called this intensity du current, or the intensity of current. So when he published his work, they took the letter I and it became standard until this day. Now you might also come across formulas where the letter E is used instead of V. The letter E stands for EMF, or electromotive force, but don't worry about that. Just stick to using V and substitute V for E if you see it used in Ohm's law questions. Anyway, so by covering V, we get voltage equals current multiplied by resistance. If we want to find current, then we write down I equals, and then we cover up the letter I in the triangle. That gives us V and R. So as V is above the R like a fraction, we can write V divided by R. Therefore, current is equal to voltage divided by resistance. If we want to find resistance, then we write down R equals, and then we cover up R in the triangle. That leaves us with V and I, so we write V divided by I, which gives us resistance equals voltage divided by current. Let's look at some examples for how to use these formulas. First, let's see how we find voltage and how it relates to the other parts. Let's say we have a simple electrical circuit with a battery and a resistor. We don't know what the voltage of the battery is though. The resistor is 3 ohms, and when we connect a multimeter into the circuit, we see that we get a reading of 2 amps of current. We want to find the voltage, so using Ohm's triangle, we can cover up the V, and that gives us V equals I multiplied by R. We know the current is 2 amps, so we can write that in, and we know the resistance is 3 ohms, so we can write that in also. Therefore, 2 amps multiplied by 3 ohms gives us 6 volts. The battery is therefore 6 volts. Now if you want to check your answers for Ohm's questions, then I've built a free calculator on the website. You can just drop your numbers in and it will do the calculation for you. Links for that again in the video description down below. Coming back to the circuit, if we now double the voltage by connecting 2 6-volt batteries in series, we get 12 volts. If we now connect this to the same circuit, the current also doubles from 2 amps to 4 amps. If we double the voltage again to 24 volts, the current will also double to 8 amps. So what's the relationship here? We can see that current is therefore directly proportional to voltage. If we double the voltage, we double the current. Remember, voltage is like pressure, is the pushing force in the circuit. It pushes the electrons around the wires, and we place things like lamps in the way of these electrons so that they have to flow through these, and that causes the lamp to light up. By doubling the voltage, we see that the current also doubles, meaning that more electrons are flowing, and this occurs as we apply more pressure or more voltage. This is just like if we were to use a bigger water pump, then more water will flow. Okay, so what about finding current? Let's say we now have a 3 ohm lamp connected to a 6 volt power supply. To find the current, we write down I equals, and then we cover up I in the triangle. That gives us V divided by R, so current equals voltage divided by resistance. We know the voltage is 6 volts and the resistance is 3 ohms, so the current is therefore 2 amps, and that's what we see on the multimeter. So we saw what happens when we use a resistance of 3 ohms in the circuit. But if we double the resistance to 6 ohms by placing another 3 ohm lamp into the circuit, the current halves to just 1 amp. If we double the resistance again to 12 ohms, the current will halve again to 0.5 amps. We can visually see this because the lamps will become less bright as the current reduces from the increase in resistance. So what's the relationship here? We can see that the current is inversely proportional to the resistance. When we double the resistance, the current will decrease by half. If we halve the resistance, the current will double. Current is the flow of electrons, or the flow of free electrons. For us to make this lamp shine, we need to push electrons through it. How do we do that? We apply a voltage across the two ends. The voltage will push the electrons. The atoms inside the copper wire have free electrons in their valence shell, which means they can very easily move to other copper atoms. They will naturally move to other atoms by themselves, but this will be in random directions, which is of no use to us. For the lamp to turn on, we need lots of electrons to flow in the same direction. When we connect a voltage source, we use the pressure of the battery to push the electrons through the circuit all in the same direction. For example, to power this 1.5 ohm resistive lamp with a 1.5 volt battery requires 1 amp of current. This is equal to 6,242 quadrillion electrons passing from the battery and through the lamp every second. And if it can achieve this, then the lamp will stay at full brightness. If the voltage or current reduces or the resistance of the circuit increases, then the lamp will become dimmer. Okay, now let's look at finding resistance. Say we have a resistive lamp connected to a 12 volt power supply. We don't know how much resistance is adding to the circuit, but we measure the current as 0.5 amps. To find the resistance, we write down R equals, and then we cover up the R in the triangle. We're left with V and I, so resistance equals voltage divided by current. We know the voltage is 12 volts and the current is 0.5 amps, so 12 divided by 0.5 gives us 24 ohms of resistance. Resistance is the opposition to the flow of electrons. It tries to prevent electrons from flowing. That's why we use resistors in circuits to reduce the current and protect components such as an LED. If we try to connect an LED directly to a 9 volt battery, it will blow out because the voltage and the current are too high. But when we add a resistor into the circuit, then these are reduced, so the LED is protected and will shine brightly. So given the circuit, we can increase the current by increasing the voltage, or we can also increase the current by reducing the resistance. We can also reduce the current by increasing the resistance.
Electrical circuits. An electrical circuit consists of an organization of elements for the storage, transmission, and conversion of energy. Energy enters a circuit through one or more sources and leaves through one or more sinks. The source energy is transformed from the thermal, chemical, electromagnetic, or mechanical form into electrical form. In the sinks, a reverse procedure takes place. In an electrical circuit, energy is transported through the agency of electrical charge and through the medium of magnetic electric fields. There are different types of circuits, parallel and series circuits. Series and parallel circuits. Series circuit has a single path for the flow of current. In an electrical circuit, components are arranged in a line. When resistors are put in a series circuit, the voltage across each resistor is different even though the current flow is the same through all of them. and if one component breaks down, the whole circuit will burn out. While parallel circuit has multiple current pathways. In electrical circuit, components are arranged parallel to each other, and other components will function even if one component breaks down. Each has its own independent circuit. Electrical work can be done without the right tools and equipment. As the basic tools and instruments have been improved over the years, a new specialized tools and instruments are developed. Here are some of the basic tools and equipment in electricity. We have pliers, screwdrivers, measuring tools, wire strippers, ammeter, galvanometer, shunt, clamp meter, and voltmeter. Electrical technicians require electrical measurement equipment to check the electrical activity and to detect the presence of voltage or current. By using this instrument, we can measure electrical parameters such as voltage, frequency, current, factor, and resistance. First on the list is pliers. It will be used for bending, twisting wires whenever you are making screw terminal connections. Pliers are available in different types, shape, and sizes. They are also available in both insulated and uninsulated handles. Uninsulated handles should be used when working on or near hot wires. It is also used for cutting big and small wires. Screwdrivers. Electricians keep screwdrivers with them at all times for removing and installing cover plates, outlets, switches, and many other devices. It's best to have a few different lengths of Phillips screwdrivers. Screwdrivers with insulating rubber jackets covering the handles are designed for better safety when doing electrical work. Measuring tools. It is used for all kinds of field measurement, such as setting heights for switches and outlets, centering lights figures, box, and marking surface. Wire strippers are used to cut and strip insulation from electrical wires. It has a row of gauge holes for stripping wires of different sizes, and it usually includes cutting jaws for trimming the wire ends. Some types are combination tools that can also be used to crimp wires and strip the vinyl jacket of an M cable. Ammeter. In order to measure the current, it must flow through the ammeter. So the ammeter must be placed in a series with the measure branch, and it must have low resistance so that the alteration of the current can be avoided, which is measured. The ammeter is connected in series to the device, which is to be measured because objects in series have the same current. Scan the quick response code to learn more on how ammeter works and used in electricity. Galvanometer was the first type of ammeter. It is used to detect and measure electrical current. A galvanometer can read direct current flow. The magnetic field created as current flows through a coil acts on a spring, which will move the needle indicator. Scan the quick response code to learn more on how galvanometer works and used in electricity. Shunt. A shunt can be used in ammeters to measure large current. It acts as a resistor that know the quantity of resistance is used to obtain an accurate reading. Scan the quick response code to learn more on how shunt works and used in electricity. Clamp meter. With the help of the current transformer, the reading will be taken. There are two types of clamp meters. AC clamp meter, which is used to measure the alternating current, and a DC clamp meter, which is used to measure the direct current. Clamp meters are used to measure the current flowing through a conductor. Scan the quick response code to learn more on how the clamp meter works and used in electricity. Digital voltmeter. Digital voltmeters can measure the AC and DC voltages, and it displays the result in converted digital form with decimal point and polarity. A voltmeter can also be considered as an ammeter. They also measure the current. Voltage is only measured when the current is transmitted in circuit through resistance. Voltmeters are capable to measure the current, voltage, and resistance, and termed as high resistant, and ammeters can also measure DC and AC. A voltmeter can measure the change in voltage by 2 points in electrical circuits that are connected in a parallel with the portion of the circuit in which the measure is made. Voltmeters have much high resistance so that it won't have any effect on the current or voltage associated with the circuit. Scan the quick response code to learn more on how digital voltmeter works and use in electricity. Multimeter. Multimeters can be used to make various electrical measurements. They can be used to measure AC and DC voltage, AC and DC current, and resistance. It is known as a multimeter because it can do functions of various meters such as voltmeter and ammeter and Ometer. Multimeters can also be used to check the continuity. Multimeters are of the two types. There are analog and digital multimeters. Analog multimeter has an analog scale, and they are also less accurate, while the digital multimeter and the reading are in digital and they are more accurate than analog. Scan the quick response code to learn more on how multimeter works and used in electricity. That concludes our 4th unit, and see you in the next chapter of this MOOC. Again, I am Sir Jormil Arangeles, your TLE buddy. Thank you.